This course is a complete revamp of the old 115BL. Our emphasis is on RF and wireless design. So hopefully the course will excite you to go and take more advanced courses as a graduate student or as a practicing engineer later. There are 4 handouts. Make sure you have a copy of each. Course information, the instrumentation setup, the homework number 1 and lab number 1. This course is worth 4 units, so we will have, in addition to experiments and lecture, homeworks, exams, and of course your notebook. So let's go over the first handout, just in general principles. You see my coordinates on top. The email address for me and Long is eu115bl2013@gmail.com. If you send email to our UCLA emails, our filters may remove it, so it's best to send email to this one. We check this one once a day around 6 p.m., so we will reply at that time. So the longest you have to wait is probably 23 hours and some minutes. Long will have office hours I will have office hours for you. You are section number 1, so from 12 to 2 on Fridays. And then Long will have office hours from 6 to 8 p.m. on Wednesdays. We chose this late hour to make sure that it doesn't coincide with the other classes. And this has 2 purposes. Number 1, you can come and ask questions. And number 2, in a rare case, when you miss some parts of an experiment, you cannot finish it in the time here, you have a second chance to come around that time and try to finish it. Okay? We don't want to make a habit out of it, but it's a second chance. All right? Then the grading is 25% for midterm, 25% for final, 20% for homeworks, and 30% for the lab notebook. As you saw in my email, you need 2 notebooks, one for the lecture notes and one for the lab notebook. What you will do is that from next time when you arrive, you give your lab notebooks to Long, and he will do a quick check. He will initial it and date it and give it back to you before you start your next experiment. This ensures that you are keeping up with your lab notebook, you're not letting anything slip. So as you can see in the considerations here, I want you to write down everything that you see, you do, you learn in the lab, in your lab notebook. If you make mistakes, it's perfectly fine. Engineers make mistakes, no problem. It doesn't make you any less of an engineer. So you forgot to turn on the power supply. Oops, you forgot to turn on the power supply. No problem, write it down. It's okay, it's perfectly fine. So my hope is to see the evolution that you go through this whole quarter through what I did in your notebook. So your notebook is a critical part of your output in this course. I do not ask for lab reports because lab reports, to make them pretty and so on, take a lot of time. And my emphasis is on substance, not appearance. So because you have to do homework and prepare for exams, I don't expect you to write lab notes and lab reports. But you make sure your handwriting is legible so that we know what you're writing, what you're talking about. When you do a measurement, like from today, right on top, experiment number 1, lab number 1, put the date on it, sketch a quick drawing of what the setup should be, and then go ahead and measure the numbers, write down the numbers, make a little table, and then eventually turn it into a plot. It's all done by hand. It doesn't have to be precise, doesn't have to be pretty, but we just want the result to come out. Okay? Sometimes you may need a screen capture from the laptop, as you will see later. So you do a screen capture, you store it on your USB, you take it home, and then you print it, cut and paste it in your laptop. Very simple. And finally, as I said, you turn in your lab notebook to Long when you arrive so that you can check it. All right. There's a recommended textbook, RF Microelectronics. It's only recommended, it's a graduate course, so we don't expect you to know all that stuff. But in case you need some reference to look at some of the concepts or familiar yourself more, you're welcome to get that book. There will be 4 homeworks in this course. You see the due dates for these homeworks. The first homework, as you can see, is relatively long, and you have 2 weeks for it. You should start this weekend with a long homework. And some of the problems are also designed so that you can't do it on your own. You have to come and ask the TA or ask me, or look it up on internet, or look it up in the book. Okay? Like the first problem, second problem are not things that you know right off the bat, and I'm not going to talk about them here. So this will encourage you to expand your horizon, learn a little more in this class than what we teach on the blackboard or on the whiteboard. Then there's a midterm exam on May 17th, and the final exam will be on Tuesday, June 11th. Any questions about the logistics of the class so far? Yes?
How long will the midterm exam and final exam be?
The midterm will be probably 2 hours, an hour and a half to 2 hours. So we might spend some of the time doing lab experiments and then the rest of it on a midterm. And the final exam, 3 hours, standard. Any other questions? Okay, if you turn to the other side of the page, you see the outline of the course. We start with some introduction to wireless communication. That's today's notes, as you can see on this board. Then we'll talk about RF instrumentation to familiarize you with the instruments that we will use throughout this course. Then we go to RF transmitters, in particular frequency modulation. We'll talk about voltage control oscillators as a means of frequency modulation. Then we talk about the concept of spectrum and phase noise, and go on to RF transmitters, discharge and amplitude modulation. Then we'll switch gears to RF receivers, talk about down conversion and demodulation, and finally power amplifiers and phase lock loops and synthesizers. So the objective here is to talk about the theory for like an hour, and then try to do the experiment in 2 hours, 3 hours, okay? Something like that. And so the theory tells you what is going on in the modules that are going to hook up to each other to build the system. And eventually, sometime in your future life, you can also try to see what's inside the modules. In practice, how do you build the device inside the modules? And that's a different course, a more advanced course. All right, any questions about the outline and the contents? All right. Okay, so moving on. We're going to talk about some basic concepts. This is a review of what you should know from, I don't know, signal systems and the sophomore, junior courses. In particular, we'll look at signals in time and frequency domains, and talk about impedance matching a little bit. Then we'll spend some time on RF instrumentation to familiarize you with the equipment that we use here for measurements. All right? So you guys in the back may not be able to see the whiteboard, so you can come forward so that your angle is better, you can see the whiteboard. Okay, so let's begin by a general introduction to RF and wireless. Is it hot in here or is it my imagination? Okay. The objective of this course is to learn how a wireless system, such as your cell phone or your Wi-Fi system, works. And by how, we don't mean a 10-minute, 15-minute study, we mean a 10-week study. So we go into pretty good detail in understanding of the journey that your voice takes, as it starts from the microphone, when you speak to it on your cell phone, it travels through the air and arrives on the other side, goes through some processing, and eventually comes on the speaker on the other side, right? So a lot of processing happens to the signal, and we want to delve into those. Of course, with only the background that you have here, you're senior level students probably, so we assume you have some background, but not too advanced. So we have to keep the study, the level of study at that point. All right, so here's the general view that you might think of if you sit down and ask yourself, what happens to the signal? We start out with the microphone. The microphone, you speak to the microphone, and the microphone generates a voltage as a function of time. So some V of t. Right, this is a low frequency signal, a few kilohertz, 4 kilohertz, 5 kilohertz. Voice goes up to 20 kilohertz, but the microphone doesn't have a good response. Then this signal goes through a transmitter, which we will call from now on TX. So a lot of things happen in this transmitter, and hopefully you'll understand some of those by the end of this quarter. And then the transmitter drives an antenna. So the antenna takes the electric signal that we have here and converts it to an electromagnetic signal out here, right? So it's a wave, and that wave propagates through the air. So the wave now propagates through the air, and it travels for a mile or something. and it comes and is picked up by the receiver on the other side. So the receiver has an antenna, and now the signal arrives here. It's a weak signal, and now the receiver has to do sort of the reverse, right? There should be a lot of processing here through the receiver, which we call Rx, so that eventually, hopefully, we can retrieve the voice signal that we transmitted. So at this point in time, at this point in the receiver, hopefully we have the same signal. And that signal now is applied to a speaker, and you hear that, and you can communicate. Okay, so at the highest level, that's what a wireless system looks like. All right, well, so there are many interesting questions that arise here, right? What exactly do we need to do to this voice to bring it to this antenna? You have learned in 115A, 115B, mostly about amplifiers, right? You can design amplifiers, you can get a frequency response, apply feedback, and so on. But is that enough? Can I just put some amplification from here to here and build a transmitter? As we will see, no, that's not enough. We need other functions that you probably have not seen in previous courses. Similarly for the receiver. Okay, the signal received here is weak, so we do need to amplify it. But will amplification be enough? And the answer is no. Again, just because here we had some processing of the signal, we have to sort of do the inverse of that processing. The inverse of the processing is not just amplification, but a lot more stuff. So those are things that we want to discover in this course and then try to build and duplicate in experiments. All right. So those are some of the principles that we will be following, right? Trying to dig in this transmitter, dig in this receiver, and see how it goes, and then eventually build stuff. Any questions about the general introduction? Okay, now to get there, we do need to go through some basic concepts that at this point, in this lecture, may seem totally irrelevant. Okay, so you have to bear with me and go through these carefully so that we establish a foundation, refresh your memory, and once we're comfortable with these, then we can start doing measurements and building these transmitters and so on. So let's talk about basic concepts. I'm going to start with signals in the time domain. Okay. Well, you know, a signal can vary as a function of time. Like the voice that we just saw is a voltage as a function of time. So we might call it x of t. And x of t has some behavior as time goes by. They go up and down. And we could try to analyze it. We could try to capture this in the time domain and look at it and try to decipher it. In this course, we'll consider one specific example of signal in the time domain, namely a periodic signal, the signal that repeats itself. So we will consider this specific case. A periodic signal. And what this means is that we have a signal that repeats itself, right? It has some form, so let's say this form up to here, and then repeats. So this form, this one. It repeats with a period of some value. So from here to here, there's a period, and this period we will call T1. So that's the period of the signal. It repeats every T1 seconds, and repeats exactly. So that's what we call a periodic signal. Okay, now what is interesting about the periodic signal is that it can be written in the form of a bunch of sinusoids. And what we know is that Fourier series represents that. So Fourier discovered that if you have a periodic signal, so call this x of t, then that x of t can be decomposed in the form of just a bunch of sinusoids. So Fourier said that you can write x of t as a summation of some amplitude times cosine of n omega 1t from n equals 0 to infinity, plus some other amplitudes times sine of n omega 1t, n equals 0 to infinity, And maybe one of these should be n equals 1, doesn't matter. And omega 1 in this case is the frequency of this periodic behavior. And it would be 2 pi over T1. All right. I want to say right off the bat that you should not forget that omega and f are related by 2 pi, okay? Everywhere in every circuit, every equation. So make sure that you don't forget that factor of 2 pi. So let's examine this. We've seen this a number of times in our past, but the key point here is that it says, Fourier says, if the signal is periodic, you can drive it in the form of a bunch of cosines and a bunch of sines. But more profoundly, each of these has a certain frequency that is an integer multiple of the fundamental frequency. Right? So you have omega 1, 2 omega 1, 3 omega 1, and that's it. You don't have 1.5 omega 1. You have only integer multiples of omega 1. So the beauty of Fourier series is that it can take any signal of any shape, as long as it's periodic, and reduce it to a summation of sines and cosines. And in fact, if I have some coefficient times cosine of n omega 1t, and some other coefficient times sine of n omega 1t, and I'm adding them, I can always convert cosine plus sine to 1 cosine plus phase. So I can write that as something like this, Cn cosine of n omega 1t plus phi of n equals 0 to infinity. So that's even simpler, right? It says that if you have a periodic signal, you can always decompose it into a bunch of cosines. And the important point about these cosines is that they all have frequencies that are multiple integers of the basic frequency, omega 1. So we will call these harmonics. Okay, so these are called harmonics. For example, C1 cosine of omega 1t plus phi 1 is called the first harmonic. First harmonic. Also known as the fundamental. And then cosine of 2 omega 1t is called the second harmonic, 3 omega 1t is called the third harmonic, and so on. So what this means is that any periodic signal can always be written as a summation of a bunch of harmonics. Right? So that's the final result that comes out of Fourier. So any periodic signal can be decomposed into a summation of harmonics. So that's a very important result that we will see frequently in our RF design work. Any questions so far? Okay. So that's really all we had to say about time domain behavior of signals. Now we're going to switch to frequency domain. As you will see in RF design, we often use frequency domain because it gives us a better understanding of the nature of the signals. Time domain analysis is not very common in RF design. Okay? So frequency domain is a much better environment. So signals in frequency domain. Okay. So, what do we know intuitively about frequency domain? Here, I plotted the signal as a function of time. So that makes sense, right? Goes up, comes down, that's one, at some rate. But in the frequency domain, do we have any intuition? So one intuition is the following. We know that, for example, when you have a high-pitched voice, it has high frequencies. When you have a low-pitched voice, it has low frequencies. Like on a keyboard, on the piano keyboard, right? You press the keys on this side, they have low frequencies. You press the keys on this side, they have high frequencies, right? So that's something we know. We also know that women's voice has higher frequencies than men's voice. So if I were to plot, if I somehow measure the signal, the voice of a woman in the frequency domain, what I should see is maybe something like this. There's some components here, some components here, etc. So that would be women's voice. And if I measure a man's voice, it's probably doesn't make it all the way to this frequency. It's lower frequency. So 0 is here, it's probably somewhere around here, right? So that's a man's voice. That's a man's voice. So man's voice might have maximum energy around maybe 1 kilohertz, whereas a women's voice may have maximum energy around, I don't know, 5 kilohertz, right? So again, we don't know exactly what this all means, but intuitively, that's what we would feel, right? That when we say frequency domain behavior, we mean how much energy do we have at different frequencies, right? You can also remember the keyboard concept, okay? So the piano keyboard, you press the keys on the left, you're over here, you generate something here. You press the keys on the right, you generate something over here, okay? So that's what it is. But mathematically speaking, a tool that allows us to go from the frequency domain to time domain is the Fourier transform. So Fourier transform of x of t, which we denote by x of f, takes us from the time domain to frequency domain. So if in the time domain, the signal is changing really fast, then we're saying in the frequency domain, it has energy at higher frequencies, right? So what intuitively we feel is that if you have a signal that's changing slowly in the time domain, its Fourier transform has something at lower frequencies, right? So now we don't know exactly what this is, okay? Don't worry about it for now. And if you have a signal that varies really quickly, then what should happen is that it has energy somewhere up here, right? So that's what we know about Fourier transform and frequency domain. So we will use this extensively in our work, and in particular for periodic signals, as we will see. It becomes a nice tool to use. It allows us to simplify things and do the calculations much more quickly. But that is the basic idea. So let me go over some examples of Fourier transform, which you have seen in the past, because we will need these also. So examples. If we have a cosine of omega 1t, a simple cosine with the frequency of omega 1. The Fourier transform of that, Fourier transform, consists of two impulses. So let me just call this omega. 0, one impulse at plus omega 1, one impulse at minus omega 1. And the area under each impulse is a over 2. So I hope you remember these from your basic signals systems. If you don't, please spend this weekend refreshing your memory, okay? It's all necessary stuff for our course, so it's important that you be comfortable with it. So what this says is that if you have a simple cosine, all the energy of the signal is squeezed at the one frequency, omega 1. At other frequencies, they have no energy. And that's what makes sense, right? It's a periodic signal, and it's pure. A sine is the purest waveform of a signal, so it has energy only at one frequency, it doesn't have any other frequency. How about a sine? A sine of omega 1t? Well, there's only a phase shift between these two. So when you take the Fourier transform, what you will see is the frequency that does not change, so we still have to have energy only at these two frequencies. But because of the phase, this becomes plus j a over 2, and this becomes minus j a over 2, j being our square root of minus 1. But the frequencies are the same as before. So you need to memorize these things, okay? You need to be very comfortable, very proficient with these spectrum, with these Fourier transforms. All right? So that's for cosine and sine. How about a constant voltage? So if you have x of t equals just a voltage, constant voltage, right? As a function of time. What is the Fourier transform of a constant voltage?
Zeros.
Zero.
At zero, there's a V naught.
There's an impulse at zero, exactly. So the Fourier transform has to be only at zero frequency, because there's no frequency, it doesn't change, right? So we have an impulse at zero with an area of V0. So that's all we have in terms of frequency content for a DC signal, a constant signal, right? Okay, very good. So, let's make two observations and arrive at a very interesting conclusion. Observation number one, Fourier says that any periodic signal can be written as a sum of harmonics. Right? The sum of cosines only. And observation number two, a cosine has a Fourier transform that consists of only two impulses. Right? With these together, it means that for any periodic signal, the Fourier transform can consist of only impulses. Because the Fourier transform of a periodic signal is the Fourier transform of this. And this has only cosines. Cosines have in their Fourier transform only impulses. So when you take the Fourier transform of that, which is the Fourier transform of a bunch of cosines, you get only impulses. So that's the way we actually identify a periodic signal. If you look at the Fourier transform and you see only impulses and nothing else, there's nothing in the middle, no other shape, then we know that it has to be periodic. It has to repeat itself. So that's how we discover periodicity in signals. For example, if you're studying, I don't know, galaxies far away and they have some periodic behavior, that's the way you look at the spectrum coming from them and see if there's anything that looks like an impulse. So, the Fourier transform of a periodic signal contains only impulses. This comes from the Fourier series and the Fourier transform, right? So Fourier series says, if it's periodic, you should be able to write it in the form of cosines, all functions of all multiple integers of omega 1, and Fourier transform of a cosine is always two impulses, so we can have only impulses. All right? Okay, that's a good and useful observation. Any questions at this point? Make sure that I cover what I want to cover so far. All right. Now, another important property that we need to understand and be able to use efficiently is the following. So the Fourier transform of a product x1 of t, x2 of t is equal to the convolution of the Fourier transforms. So it will be equal to x1 of f convolved with x2 of f. As you will see, in many cases, we do end up multiplying signals in the time domain in RF design. So that means that if you understand the Fourier transform, a quick way of finding the Fourier transform is to do this. You find the Fourier transform of the first signal, you find the Fourier transform of the second signal, and you convolve them.